Hello, my name is Vitaly Kamaridis, and this is Electronics 1 with Dr. Mateo Boy. So, for the presentation portion of the class, I went ahead and decided to do my Lab 5, which is BJT Amplifiers. So, here is a quick outline of my lab. So, the lab objective, circuit analysis, CAD simulation, experimental results, my results, and a discussion and conclusion. So the objective of this lab was to design a basic common model of mode emitter bipolar junction transmitter amplifier, or short for CE-BJT amp, with a maximum load current of 1 milliamp and a gain of -10. So this is the basic design of my BJT amplifier that I created in LT-Spice. And here are my calculations that I've used in order to complete this lab. I went ahead and used the values that were given, or the design requirements, and then plugging those values into my equations and solving for it. Here is the graph of a collector current. This is a simulation. So moving into my CAD simulation of this portion of the lab. Here are my DC bias points that I used. So I got this off of LT-Spice. And this is my gain that I got from graphing it in LT-Spice of my BJT amplifier. And then here is the frequency response graph. This is the load resistance sweep graph. And so just a quick note that I left at the bottom was the R load range is greater than 100 ohms. That was like a note for myself. And here is the temperature analysis graph between 0 and 80 degrees. And this is my input impedance graph. And the output impedance graph, so 7.4 kilo ohms. That's what I got for R's of out. So here is a graph or a table for the experimental results of my DC bias points. So for the collector, I got 7.07 volts. For the base, I got 1.63. And the emitter, I got 1.05 volts. So here's the experimental gain that I got for the BJT amplifier, and there's a image of my design that I built on the breadboard, and then I ran it through an oscilloscope and got that graph. Here is the frequency response graph. This is all the experimental portion of my lab. load range. Okay, so here is the comparison or the results that I compared between my theoretical simulation and experimental. Oh, whoops. Then my air percentage air. So it shows that I got pretty for my theoretical stimulation. It was a pretty good low air. So the discussion portion of my lab. So I have designed a common emitter amplifier with a gain of -10 using a single power supply of 50 volts and a quiescent collector current of 1 milliamp. The DC bias points and gain obtained through simulation experimentally were expected. So I got what I was expecting. Although these values obtained through experiment had a larger percentage percentage error. This was expected because the resistors used were not the exact value since I had to connect some of those resistors in series in order to obtain the similar resistance that I calculated in the experimental portion of the lab. I had noticed that in the simulation that the temperature variation between 0 and 80 degrees had very small variation in output gain for the voltage input I had, but when it was increased the voltage there was more noticeable variation, and this is due most likely to the resistance not being swamped. When I did a sweep of load resistance I had saturation when the load resistance dropped below 100 ohms. I think this was due to the collector voltage maximum of swing being affected and that the collector voltage needed to be greater than 0.03. So, in conclusion, to summarize this lab, I have designed, built, and simulated the common emitter amplifier, or BJT, with a gain of -10, which was accomplished. And the important note is that the gain is negative because the output voltage is measured and the collector side, and the voltage at the collector is negative with respect to the current. Another point that I mentioned is the results obtained through the theoretical analysis, simulation, and experiment are all agreed with a low margin of error. Thus, I had successfully demonstrated the behavior of a rectifier circuit. The common emitter amplified voltage but needs to be biased correctly for the circuit to work. So here you go.